So this is the fifth video on section 7.7, triple integrals. And here we're going to integrate over the tetrahedron bounded by these four vertices. So we have the origin, 3, 0, 0, 0, 4, 0, and 0, 0, 5. We're going to integrate this polynomial here over our region R, and R is the tetrahedron bounded by these four vertices. Drew a picture here. So here is 3, 0, 0, 0, 4, 0, 0, 0, 5, and of course the origin here is back in the corner. So that's our tetrahedron. So what we would like is the equation of the plane that passes through the point 3, 0, 0, 0, 4, 0, and 0, 0, 5. So remember how to do that? How to find the equation of a plane passing through 3 points. Find a vector with these 2 points. Find another vector with a different set of points. Take the cross product of the 2 vectors. That's your orthogonal vector to the plane. Then use one of these 3 points to find the equation of a plane. Show you a little shortcut with this one though. Because we have a point on the x-axis, on the y-axis, and the z-axis, look at 3, 4, 5. Take the product. 3 times 4 times 5 is 60. So we're going to have a coefficient x plus coefficient y plus a coefficient z is equal to 60. And now let's figure out what those coefficients are. Well, because 3 times 20 is equal to 60, and the point 3, 0, 0 is on our plane, our x coefficient is 20. Because 4 times 15 is 60, and the point 0, 4, 0 is on our plane, the coefficient for y has to be 15. And likewise, the coefficient for z has to be 12, because 12 times 5 is 60, and the point 0, 0, 5 is on our plane. So that's a little bit of a shortcut of finding this plane. Reason we're doing this is now we're setting our tetrahedron up as a type 1 region in R3. That means our projection onto the xy plane is this triangle down here with vertices, the origin, 3, 0, and 0, 4. Or we could say 3, 0, 0, 0, 4, 0 if we want to think of those in R3. So we have a type 1 region in R3. And so our bottom function is simply 0. So we start at the xy plane and we go up to this plane here. And so we take the equation of the plane, solve for z in terms of x and y. So z ranges between 0 and this function. That is in R3. But remember, after we calculate our integral with respect to z, now we have a double integral in R2. That double integral is bounded by this triangle. Passes through the point 3, 0 and through the point 0, 4. So we find the equation, the line passing through the points 3, 0 and 0, 4. And that's negative 4/3 x plus 4. X ranges from 0 to 3, right here. And so we've also set this up as a type 1 region in R2. And so now we've set up our integral. So z goes from 0 to this function. And we take our 108x plus 216, find an antiderivative with respect to z. So that's not so difficult. Substitute this expression for z, substitute 0, and subtract. It simplifies to this. And now we have a function of 2 variables, x and y, and we have this set up as a type 1 region in R2. So y goes from 0 to negative 4/3 x plus 4, x goes from 0 to 3. Now we find an antiderivative with respect to y. Substitute negative 4/3 x plus 4 in for y, substitute 0 in for y, subtract. I've skipped some steps here. But after you do that, it simplifies to the integral from 0 to 3 of this polynomial. This is a 3rd degree polynomial. So, as I've said before, now we have a Calc 1 problem. Find an antiderivative, substitute 3, substitute 0, subtract. We have 2,970. And so again, just to save time and to save space, I've skipped some steps here, so I'm going to let you work out the details at home.